Ladies and gentlemen, we are looking at notes 3.1, which are on operations on radicals. So the first thing I want you guys to do is to fill in the following chart. And I'm going to actually have you pause the video and see if you can fill in as much as you know without a calculator. So don't use a calculator to fill this in. I want you to see what you know. And then when you come back, if you have to leave any blank, that's totally fine. When you come back, circle the ones that you still didn't know or the ones that you got incorrect, because you're going to need to study those because you're going to have these memorized. Okay? All right, these are the values that you should have gotten. Again, please highlight or circle the ones you either got wrong or the ones you didn't know. And this is what your first mini quiz is going to be on this unit. I'm just going to give you a chart that looks exactly like this, and you're going to have to fill in the perfect squares. Memorizing the perfect squares are going to make your operations on radicals so much easier. So now, what is a radical to begin with? A radical is just a root. And for the purposes of this class, we're only going to deal with square roots, but there are other kinds of radicals like cube roots, fourth roots, fifth roots, so on and so forth. But we're going to just look at square roots. All right, so how do I simplify a radical? So an example that's given to you here is the square root of 80. If I asked you to find the square root of 16, for example, you could tell me easily that the answer is just 4 because 16 is a perfect square. If I asked you find the square root of 25, same thing, you could easily just tell me the answer is 5. But finding the square root of 80, for example, is very difficult because it's not a perfect square. So what we're going to do here is we're going to simplify the radical. So step 1 says to factor the number under the radical sign. This number is called the radicand, okay, if possible, so that one of its factors is the largest possible perfect square. And that's key that we say largest, okay? So what I'm going to do is I'm going to make a factor chart for 80. But I'm only going to worry about the numbers that I have up here, my perfect squares. I don't care about the number 2, for example. 80 is divisible by 2, so 2 is a factor, but I don't care about 2 because 2 is not a perfect square. So we'll start with 1. 1 will work, so 1 and 80. Okay, we know the next perfect square is 4, and 80 is divisible by 4, so we'll put 4 in our chart, and 4 times 20 gives me 80. So 4 and 20 are my two factors that I'm going to add onto my list, okay? Then I'm going to try 9, and 9 is not a factor of 80 because 80 is not divisible by 9, so I'm not going to worry about 9. Then I'm going to try the next perfect square, which is 16, and 80 is divisible by 16, and when I divide 80 by 16, I end up getting 5, okay? And I'm going to keep going through my list until I get to the halfway point of whatever my radicand is. So here, since my radicand is 80, I'm going to keep going until I get to 40. So I'm going to try 25. Is 80 divisible by 25? Nope, so it's not a factor. Next, I have 36, and 80 is not divisible by 36 either, so that's not a factor. And then I can stop because all the other perfect squares are greater than half of 80, okay? So now that I've done my chart, I want to choose the largest possible perfect square. So 16 is bigger than 4, so I'm going to use 16 and my other factor, which is 5, because 16 times 5 is 80. So essentially what I'm going to do is I'm going to write this as the square root of 80 is the same thing as the square root of 16 times 5, because 16 times 5 is 80. So then step 2 says you're allowed to split up a radical sign if there's multiplication underneath it. So if you see how there's multiplication underneath my radical right here, I'm allowed to say that it's just the square root of 16 times the square root of 5, okay? Then step 3 says to evaluate the square root of the perfect square and leave the other factor underneath the radical sign. So only one of these numbers is a perfect square, and that was 16. So we're going to just take the square root of 16 and say that that's 4, and then we have the square root of 5 left over because I can't square root 5. Now, a couple notes. First of all, once you square root a number, the square root sign is gone, so you shouldn't have a radical over the 4 anymore. But I still have the radical over the 5 because I haven't square rooted the 5 yet. Second note is that people still want to take this 4 and square root it further because it's a perfect square, but there's no radical sign above it anymore, so I'm not going to square root it. So this is my final answer. Let's go ahead and try this. So in questions 1 through 3, it asks us to simplify. So I'm going to make my factor chart for my radicand, which is 200, and I'm going to go through until I get to the halfway point of 200. But we're going to be a little bit logical about this right now because the halfway point of 200 is 100. So that's the largest possible perfect square because we figured out that if we go to the halfway point, that'll give us the largest possible perfect square. So I'm not even going to bother to try all the other values because 100 is the largest possible perfect square. And then the other factor is 2. So at this point in time, you can write that it's the square root of 100 times 2 like that if you want to, or we can go straight to splitting it up because it's not necessary anymore to show it all under one radical, okay? Now, the square root of 100 is simply 10, and then the square root of 2, you can't square root it, so it's just 10 root 2, okay? All right, so now in number 2, it says that the number under the radical is 243. For right now, ignore the 5. I'll tell you what to do with the 5 in a minute. So the first thing I want to do is figure out, well, what's the halfway point of 243? So it's 121.5. So I'm going to try all my perfect squares until I get to 121, okay? So let's make a chart right here and see what's going to work. So for 243, I'm going to try 1. Obviously, 1 is going to work, okay? The next perfect square is 2 squared, which is 4. 243 is not divisible by 4. Then I'll try, and I know that because 243 is odd and 4 is even. Then I'll try 243 and divide it by 9, and it works, so I get 9 and 27, okay? Then I'll try the next perfect square, which is 16. 16 doesn't work because it's even. So then I will try the next one, which is 25. 25 doesn't work because this doesn't end in a 5, okay? And rather, the whole number doesn't end in a 25, a 50, a 75, or a 0. So 25 doesn't work. 36 doesn't work because, again, 36 is even. So I'll try the next perfect square, which is 49. So 243 divided by 49, and I end up getting 4.9 something. It doesn't work. By the way, all I'm doing is I'm going through this list right here. So I tried all of these numbers up to 49. The next number I'm going to try is 64. That won't work because it's even. So I'll try 81. So 243 divided by 81 gives me 3. So I'm going to include 81 and 3 in my list right up here, okay? Then the next perfect square is 100. 243 is definitely not divisible by 100. And then the last one we said we're going to try is 121 because the halfway point is 121.5. So 243 divided by 121, obviously I already know it's not going to work because the halfway point is 121.5, so 121, there's no way that it's going to work. So based on my list right here, I can see, sorry about that, that 81 is my largest perfect square. So I'm going to use 81 and 3. Now this 5 right here, there's nothing I can really do with it right now, so I'm just going to copy it down. So then 243, I'm going to split it up into the square root of 81 and the square root of 3. Same thing with the 5. There's nothing I can do with it right now, so I'm going to copy that down. The square root of 81, I can square root it evenly, and I get 9. Always put the perfect square first, by the way, okay? And then the square root of 3 is not evenly square rootable, so I'm going to leave it as the square root of 3. Now I can multiply the 5 by the 9, and I get 45. So I get 45 times the square root of 3, and that's my completely simplified radical. Okay, all right, now the last one that we have here is the square root of 40, x to the power of 7, y to the power of 2. So I'm going to make my chart for 40 to start off with, and I'm going to use my list of values that I have. Okay, so looking at my list, first of all, the halfway point of 40 is 20. So I'm going to stop once I get to this 16 right here. So the square, or excuse me, 1 is a factor of 40, so I can use 1 and 40. The next number on my list is 4. 4 is a factor of 40, so I'll use 4 and 10 because 4 times 10 is 40. The next number on my list is 9. That's not a factor of 40. The next number on my list is 16, and 40 is not evenly divisible by 16. So I've figured out my largest possible perfect square, and that's 4. Now, that makes the number easy, but it's the variable that makes things a little bit more difficult. So we've got 4 here on this side. This is what can be square rooted. And then we're going to put whatever can't be square rooted over here, okay? So now I want to take a look at my variables and see how I can split it up into what can be square rooted and what's left over. Now, if you remember, if I do x times x, I should get x squared. If I do x squared times x squared, I should get x to the power of 4. If I do x to the power of 3 times x to the power of 3, I should get x to the power of 6. X to the power of 4 times x to the power of 4 is x to the power of 8, so on and so forth. So if you notice, all my perfect squares for my variables have even coefficients. X to the power of 7 is not an even coefficient. So which one of these can be taken out of this x to the power of 7? Well, if I take out 6 x's being multiplied together, this means 7 x's being multiplied together, I'll still have an x left over. So that means that I can take out an x to the power of 6, and then I'll have an x to the power of 1 left over. And then y to the power of 2 already has an even exponent, so I can just leave it as y to the power of 2. So now what I'm going to do is I'm going to square root what can be square rooted. So the square root of 4 is 2. The square root of x to the power of 6 is x to the power of 3. And the square root of y to the power of 2 is just y. And then I can square root 10 and I can't square root x. So my answer is 2x cubed y times the square root of 10x. All right, so the next thing we're going to talk about is multiplying and dividing radicals. So if you notice right here, we have a root b times c root d. So essentially, all I'm going to have to do is just multiply my coefficients. So here my coefficients are a and c, so I would multiply a by c. Then I would multiply my radicands, so b times d, but they'd be under the square root sign. And then I would simplify if possible. So for example, right here, I've got 2 times 3. These are my coefficients, so I get 6. And then root 5 times root 7 is going to be root 35. And then I would simplify if this is possible, but 35 is not divisible by any perfect squares, so this is my final answer. Okay? Same thing with dividing radicals. I would divide my coefficients, so I would divide a by c. And then I would divide b by d, and that would all go under my radicand, okay? And then I would simplify again if possible. So let's look at this right here. All this is saying is my coefficients are 6 and 2. When I divide them, I get 3. And then I would divide 14 by 7, which is 2, but they're both under the radical, so my answer would be 3 root 2. I would try to simplify this if I could, but 2 is not simplifiable. The square root of 2, excuse me, is not simplifiable any more than this. So that's my final answer. Okay, so in number 4 right here, same thing. I multiply my coefficients. So 7 times 5 is 35. And then I would multiply the numbers under my radicals. So my radicands would be 2 and 6. So it would be the square root of 12. Okay, then I'll make a list for factors of 12 that are perfect squares, but I'm only going to go to the halfway point. Half of 12 is 6. So the first perfect square on my list is 1. Obviously 1 will work. The next perfect square on my list is 4. 12 is divisible by 4, so I'll use 4. And the next one is 9. That's larger than half of 12, so we don't need to even worry about 9. So we can say that 1 and 12 are factors, and we can also say that 4 and 3 are factors. We're going to use 4 and 3 because those are larger. So I'm going to copy down the 35, and then I'm going to split the square root of 12 up into the square root of 4 times the square root of 3. Well, 35 again stays 35. The square root of 4 now becomes 2. And then the square root of 3 just stays the square root of 3. So then my final answer would be 70 root 3. Okay? So taking a look at number 5 right here, same thing. I would multiply what would be my coefficients, but this time all of 2x is considered my coefficient. So 2x times 4 is going to be 8x. And then I'm going to multiply my radicands. So 8x cubed times 4x squared, 8 times 4 is 32. And then x cubed times x squared, remember when we multiply, we add our exponents. So we get 32x to the power of 5. So now let's make a list for 32. And we're going to stop at the halfway point of 32, which is 16, which luckily is a perfect square. So I don't even have to go through my whole list. I can just go straight to 16 because that will be the largest possible perfect square. So I end up getting 8x and then under what can be square rooted, I'll put 16, and then the 2 will go with what can't be square rooted. And then x to the power of 5, the largest exponent I can take out of that that's an even number is 4. So I can say x to the power of 4, and then I have an x left over because x to the power of 4 times x is x to the power of 5. So then I'm just going to copy down the 8x, and the square root of 16 is 4, and the square root of x to the power of 4 is x squared, and then I have root 2x left over. So I have 32, 8 times 4 is 32, x to the power of 3 times the square root of 2x, and that's my final answer. Okay? All right, and number 6, it says 5 root 13 squared. So that means 5 root 13 times 5 root 13. Well, if I do this right here, I'll see that 5 times 5 is 25, and then root 13 times root 13 is root 169, which is still a perfect square, so I don't even have to simplify it. The square root of 169 is just 13. And when I multiply 25 by 13, I end up getting 325, and that's my final answer. Okay? Now, one other option that you have is to just square everything inside of here. So when I square the 5, I end up getting 25, and when I square the square root of 13, I just get 13, and that brings me back to 325 here. Okay, number 7 is now division. So same idea, but we're just going to divide our radicands here, so and our coefficients. So 20 divided by 4 is 5, and then the square root of 6 divided by the square root of 2 is the square root of 3. And 3 can't be divided by any perfect squares other than 1, so that's my final answer. Okay, 56, square root of 56 divided by the square root of 7, they technically have invisible coefficients of 1. 1 divided by 1 is still 1. I don't really need to write it. And then 56 divided by 7 is 8. So I'm going to get the square root of 8 as my answer. And when I take 8 and I find the perfect square factors of 8, I'm going to go to the halfway point, which is 4. So obviously 4 is what I want to use because 4 is a perfect square. So I'm going to use root 4 and root 2, and then the square root of 4 is 2. So my answer is 2 root 2. Okay. Last one, number 9, same thing, invisible coefficients of 1, so we don't have to worry about that. 48 divided by 6 is going to be 8, so it's the square root of 8. And then when I divide, remember we subtract our exponents, so it's the square root of 8x to the power of 5. Well, we already have our chart for 8, so that's convenient. So when I do my radicals right here, I'll use 4 as my perfect square, and then I'll use 2 as the factor that's left over. And then x to the power of 5, the highest exponent I can take out of there that's even is x to the power of 4. And then I have an x left over, just like we had up here, because x to the power of 4 times x is x to the power of 5. So then I end up getting 2, square root of 4 is 2, x to the power of 2 times the square root of 2x. All right, hang in there. We're almost done. We're going to talk about adding and subtracting radicals now. Really quickly, just a reminder, if I gave you like 8x plus 3x, you'd be able to put it together and tell me that it's 11x. Or if I gave you 7y squared minus 5y squared, you'd be able to put that together and tell me it's 2y squared. Or if I gave you 5/9 plus 3/9, you could tell me that put together it gives you 8/9. Because whenever we add or subtract values, they have to have things in common. We're putting things that are like each other together, that are in common together. So in order for us to be able to add or subtract radicals, they must be like terms as well. And what makes them like terms? They have to have the same radicands. And remember we said radicands are the numbers under the square root. So they have to have the same radicands in order for us to be able to get this to work for us. So for example, in number 10 where it says to simplify, we've got 2 root 3's and we're adding 5 root 3's. So if I've got 2 of something and 5 of something, it's like I have 7 of that same something. So it's kind of like if I have 2x plus 5x, I would get 7x. But here the x is kind of like, the x is essentially our root 3. So what this means is that my answer here is going to be 7 root 3 because I've got 7 sets of root 3 in all of my terms altogether. In number 11, the number under the radicand here is, the number for the radicand here is 5, and the radicand here is 7. So they don't have the same radicands, which means that they're not like terms. Sometimes I can get them to be like terms. So for example, if I had 1/2 plus 1/3, at this point in time, I can't put them together, but I can force them to go together by getting a common denominator. So if I can get a common radicand, then I can add these guys together. If I can't, then it's impossible. So like with fractions, you can always get common denominators. With variables, if they're like each other, they're like each other. If they're not, you can't do anything about it. With radicals, sometimes you can get it to work and sometimes you can't. How do I get it to work? By simplifying my radicals. So if you look right here, the number under the radical is 5. The number under the radical here is 7. I can't simplify 5 any further, the square root of 5, and I can't simplify the square root of 7 any further. So that is my final answer. This is as simplified as it's going to get, okay? Now, in number 12, however, we've got 4 root 27 plus 5 root 12 plus 8 root 75. I'm going to see if I can get these guys to get the same radicands, okay? So what I'm going to do is this 4 on the outside, there's nothing I can do with it, so I'm just going to copy it down. And then I'm going to look at 27 and I'm going to see, well, what number can I divide 27 by that's a perfect square? So I'm going to look at my list of perfect squares and I would go through the whole list, but eventually you're going to get to a point where you're just going to be able to identify it immediately. So when I look at my list right here, I can see, oh, 9 is a perfect square and 9 is a factor of 27. So I'm going to use 9, and then 9 times 3 gives me 27. So I'll use square root of 9, square root of 3, and then just copy down the 4. And then I'm going to copy down the plus 5, and I'm going to split up the 12. So the square root of 12, I can divide that by what number inside of my radical right here? I can divide it by 4, because 4 is a perfect square. So that means that right here I would use 4, and then 12 divided by 4 is 3. Look at that. It's starting to look pretty promising for me, okay? And then I'm going to copy down plus the 8, and then same thing with 75. I'm going to look at my list of perfect squares, and I see that 25 is a perfect square, and 25 is a factor of 75. And look at that, I get another 3. 25 times 3 is 75. So now I'm going to go ahead and square root everything that I can square root. So this 4 just stays 4. The square root of 9 becomes 3, and then I copy down the square root of 3 because I can't simplify that any further. Plus, copy down the 5. The square root of 4 is 2, so I bring that down as a 2, and then I just copy down the square root of 3 because I can't square root that any further. Plus, copy down the 8. The square root of 25 is 5, and then I've got radical 3. All right, I'm almost there. So now, if I have 4 times 3, I've got 12 sets of root 3. And then I've got 5 times 2, so I've got another 10 sets of root 3. And then I've got 8 times 5, so I've got 40 sets of root 3. So now they all are like terms, and now I can put them together. So 12 plus 10 plus 40 gives me 62, so I get 62 root 3 as my final answer. Okay?
All right, number 13 is the last one we're going to do together, and then for now, and then 14 and 15 we're going to do next time I see you guys in class. So for 13, I'm going to do the same process. I'm going to try to simplify each radical so that way I can see if I have any common radicands, because at this point in time, I don't. So first thing I'm going to do is copy down the 2x. And then I'm going to look at 20x. And 20, the largest perfect square I can divide 20 by is 4. And then I have a 5 left over because 4 times 5 is 20, okay? And then x can't be square rooted, and there's nothing else I can take out of x, so that's going to go with the 5, okay? Then I'm going to copy down the minus 4, and then I'm going to look at 45, and I'm going to see what number 45 is divisible by. Well, I'm going to go through up until the halfway point of 45, which is 22.5. So I'm going to start with 25 is too large, so I'm going to start with 16 and I'm going to work my way backwards. 45 is not divisible by 16, so that won't work. 45 is divisible by 9, so that would work. So I'm going to use 9 right here, and then 9 times 5 is 45. And then what can I take out of x cubed that is a perfect square or that has an even exponent? Well, I can take out an x squared, and then I'll have an x left over. All right, so now I'm going to copy down the 2x, and the square root of 4 is 2. Then I'm just going to copy down the square root of 5x because I can't square root that any further. Minus 4 times the square root of 9x squared is 3x, and then times root 5x. Well, this becomes 4x root 5x minus 12x root 5x. And then I have like terms. I've got like radicands here, and my coefficients here are also combinable. So when I put 4x minus 12x, I get negative 8x. So my answer is negative 8x root 5x. And I'm good to go. Okay, again, 14 and 15 we'll do together in class. Have a great day. I'll see you next time you have class. Bye.